Hi all, this is my video number 15. I'll talk on the convergence series. Convergence of series. Alright, so in the last video I have given you the introduce you what the series is. What is the partial sums, yeah, if the partial sum converge, then the series converge, and so on. Alright, so in this video I'll begin with the theorem for the convergence of the series, yeah. So the theorem, first theorem is that if the series UN converge, so that series, again with that summation means it's series, so I from 1 to infinity, n from 1 to infinity. So if it's not written, the limit there is understood that n 1 to infinity, yeah, converge, then it's not clear. Right, then the limits of UN is 0. Alright, so before I prove this this thing, that let me stress on that. So if the first thing is that the series must converge, then the limit is 0. The theorem doesn't say that if the limit 0, then the series converge. No, it's not saying that way. Alright, first the series must converge, then the limit is 0. So the other way, we might look later what happened. If the limit UN is 0, does the series converge? We look at that later, but it's not converge. Okay, not necessarily converge. So let's prove this first. So if you consider the partial sum of that series Sn, right, so we have u1 plus u2 plus up to un, and if you consider the up to n minus 1, yeah, so we have u1 plus u2 plus un minus 1. So here the series converge. What does it mean the series converge? In the last lecture we have, if the series converge, it means that the limit of Sn must give some value, let's say those value L. So that means the series converge. So if you subtract these two series, these two partial sums, what happened? So we have Sn minus Sn minus 1. So what we have, this one cancel out everywhere, except that that one. So we have that equal to un. Alright, since we know that series converge, yeah, since, let me write those things, since un converge, this means that the limit of Sn is equal to some number L, say. So n minus 1, if it converge, it gives no difference. So this is also true for limit n goes to infinity Sn minus 1. Oh, sorry. Yeah, n goes to infinity. So n minus 1. So then if you take the limit of those, so therefore, if you take the limit of Sn minus Sn minus 1, means we take the limit on the left and right side. So we have limit n goes to infinity un. So what we can see, this part here, you can split this. So we have, so let me write that as a subject. So we have limit un n goes to infinity. So this one you can write as a limit Sn minus limit Sn minus 1. Alright, so since we have that converge, so limit is equal to L, so what we have this L minus L, that give you 0. So this confirm the result of the theorem, saying that if the series converge, then the limit of the un is 0. So what happen if you have, say, limit of if un is 1 over n? Yeah, so for the sequence we know that this sequence converge, right? So and in fact that sequence converges to 0. But for the series 1 over n, this is diverge. We're going to prove this. Alright, so if you take the limit of un, limit of 1 over n, that goes to 0, but the series diverge, so it's not contradict. It's not contradict with that, but it says that if the limit un is 0, then the series not necessarily converge. But if this converge, then definitely limit is 0. So hope you can understand those things. Okay, so the converse of that theorem is not true. So which means in this case we only have one direction. The other one is not true. This direction means series converge, then limit 0, and this the not true is limit 0, then the series converge. So that one is not true. So now let's show that the series of un diverge. Okay. So we have, let's see, what we want to do now is we want to show that that series 1 over n diverge. Okay, so now we consider, in order to prove that, we consider the partial sum of S to n. That give you, we have 1 plus 1 over 2 plus 1 over 3 plus 1 over n plus 1 over n plus 1 and so on up to n. Okay, and for Sn itself, the partial sum for Sn itself, Sn, this is 1 plus 1 over 2 plus 1 over 3 and so on up to 1 over n. So if you subtract between these two, what we have, Sn minus S2n minus Sn, that will give you, so we have that one is cancel out, half cancel out with half, 1/3 cancel out with 1/3, 1n of cancel out with 1n. What left is 1 over n plus 1 up to 1 over 2n. So what left is that 1 over n plus 1 plus 1 over n plus 2 plus 1 over plus n plus 3 and so on up to 1 over 2n. So here you have as many as n terms. Alright, for each of that terms, we know that this is 1 over n plus 1 is bigger than 1 over 2n. Alright, it's bigger than. For that, bigger than 1 over 2n and so on. And we have 1 over 2n. Last term is equal. Alright, since we have n terms there, and we add up to n, so which means this is give you n over 1 over 2n, that give you half. So in this case, if you remember the Cauchy condition, that if the sequence converge, then there exists, or you can find a number n that n and m, the difference between those two sequences less than epsilon for all n and m greater than capital N, where those is small, just a small number. But in this case, we have our m. If you want to consider our m as a 2m and the other one is n, then this is equal to 2 and greater than 2. In fact, we need less than, but we got greater than 2. So it's not satisfy the Cauchy condition. Okay, not satisfy the Cauchy condition. Cauchy condition. So therefore, those series 1 over n does not converge. The sequence of Sn does not converge, which means our series Un does not converge. In other words, diverge. Does not converge. So in other words, it's diverge. So here I want you to remember that, because we're going to use this as our reference later on, that this series is diverge. Okay, we need to remember that series diverge. We're going to use this as a reference later on. There is an alternative proof to show that 1 over n is diverge. So I think I just leave it to you to study that part. All right. I just show one part of the proof, how to show or how to prove 1 over n is divergence series. Now, what happen if, so out of that theorem, we say if those series converge, let's say I put it equal to or converge to some number u, then the limit of un is 0. Okay, so this is the theorem, the theorem that we have discussed just now. And we have, if out of that theorem or out of that result, if the limit un is 0, then it's not necessarily the series converge to some numbers n. It's not necessarily that. But what happen if the limit of un is different than 0? Okay, so let's see a couple of examples that deal with that kind of situation. Okay, so let me give you a contrapositive example. Again, look at that. If the theorem says the series converge if the limit is 0. If the limit is not 0, what happens? We also know that if the limit is 0, it is not converge, not necessarily converge. But what happens if the limit is 0? It's not 0. Yeah. Example. So if the limit of un is different than 0, it's not saying converge, but different than 0. Even though if un converge to some values but not 0, then still we have, if that is converged, then if the limit of un is different than 0, then this series diverge. Okay, so I hope that I made you clear with that, this theorem. Okay, so let's say example. If you consider this series n over n plus 1, if you take a limit of this, limit of n goes to infinity n over n plus 1, I think this is very obvious. You can we can get strict answer for that. That gives you 1. Alright, just divide by 1 by n to the numerator as well as denominator, then take a limit, you got 1, and this is different than 0. Alright, so therefore in this case those series n over n plus 1 diverge. Alright, and the second example, if you have a series 2n over 2n minus some numbers 5, say for example, this also diverge. Since if you take the limit of those 2n over 2n, this is n, 2n minus 5, this gives you 1 which is different than 0. Alright, n goes to infinity. Okay, there are many examples like that. If you can, so I have one more here. If you consider those series 3n minus 1 over 4n minus 5, this also diverge, as if you take the limit n goes to infinity 3n minus 1 over 4n minus 5, this is equal to 3 over 5. Again, this is different than 0. So therefore those series diverge. Okay, so let me stress again. I think I've repeated many times. I have repeated many times that if the series converge, we have the limit of un is 0. But if the limit is 0, it's not necessary the series converge. Okay. And on top of that, if the limit of un is different than 0, then definitely they give you the series diverge. Okay. So look at example. Here, if the limit is 0, then it's not necessarily the series diverge. Not necessarily the series converge. Yeah, we have no conclusion for this. No conclusion, which means it could converge, it could diverge. Yeah. So let's see some example. Some other example. So if we have seen that for that series, we know that that series diverge, but the limit 1 over n is 0. Okay. If you look at the other series, let's say 1 over n squared, this series converge. And if you take the limit of 1 over n squared, this gives you 0. So I would say we cannot consider the limit is equal to 0, the limit of that un equal to 0, to make a conclusion. Cannot. Okay. And maybe you can try this as an exercise. Can you show that that series 1 over n log n diverge? Okay. Can you show this? I leave it to you. Of course, if you take a limit of this, 1 over n log n, this is 0, but the series diverge. Now, let's see a couple of properties of the series. We have a theorem. Let's say we have two convergence series, un, let un and vn be convergence series. Then un vn convergence series. Remember that if convergence means if we take a limit of the partial sum, it has a value. Then we have the sum of these two series, un plus vn. This is equal to, you can take out those sum and then add up each of those terms. And number two, if you have some constant in front of it, un, this is just equal to c un for any c constant. And number three, we have a of un plus b vn, extension of those. It just this can be written as a un plus b u vn. Alright, so let us prove this. I prove one of them. The rest you try it as an exercise. It's not that difficult, not that difficult. So proof of first part there. So since given the series converge, so we let some un, let's say those series converge to u and vn converge to v. And if we consider the partial sum of those, let Sn, that's equal to u1 plus u2 plus up to n, and Tn, another partial sum for Vn, so V1, V2 up to Vn. So if you add up those Sn and Tn, then Sn plus Tn, this is equal to, we have u1 plus u2 plus up to un and plus v1 plus v2 plus up to vn. Okay, then you can rearrange this. That gives you u1 plus v1 plus u2 plus v2 plus un plus vn. Alright, so if you take the limit of Sn plus Tn, then the properties of limit shows that you can split those things. That gives you limit of Sn plus limit of Tn. Alright, and we know that Sn converge because the series converge. Then the limit of Sn goes to u, the limit of Tn goes to v. And we know that u is the limit for the series un, and v is the limit for the series vn. Alright, so therefore we have the limit of Sn plus Tn. This is just the summation of un plus vn. So therefore we have summation of un plus vn that equal to un plus vn. Okay, that's from there. That's from the definition of the limits. I mean the properties of the limits, and then you can show, because the limit of Tn Sn, we know that this converges to u, that one converges to v, right? So for the formula number 2 and 3, I think you can try yourself, do it as an exercise. All right. So I would like to end up this video with one example. Show that one plus 1 over 3 plus 1 over 6 plus 1 over 10 plus 1 over 15 plus 1 over 21 and so on, 1 over n plus 1 over 2 and so on, this equal to 2. We're going to prove this. Alright. So first we let the partial sum of n terms, so Sn, that give us 1 plus 1 over 3 plus 1 over 6 plus 1 over 10 and so on. We have up to n plus 1 over 2. Alright. Then you can just multiply those half to the left side, so we have half Sn, that give you half plus 1 over 6 plus 1 over 12 plus 1 over 20 and so on, 1 over n plus 1. And we know that this term here, I think I've shown in the in my previous lecture, that can be written as 1 over n minus 1 over n plus 1. Of course, you can always use the partial fraction to obtain those things. All right. So which means all that terms can be written as, using this, all that term can be written as 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, okay, plus 1 over 3 minus 1 over 4 and so on. 1 over n minus 1 plus 1 over n plus 1 over n, I think minus here, minus 1 over n plus 1. So what you can see from here is that we have half cancel out with half, 1/3 cancel out with the next terms, that 1/4 cancel out with the next term, and so on. 1 minus n cancel out with the previous term, and 1 over n cancel out with 1 over n. So what left is that 1 and 1 minus 1 over n plus 1. So what left is 1 minus 1 over n plus 1. So if you take a limit of this, so limit of half, I can put it there, of Sn, that gives you limit of those things, 1 over n minus n plus 1. That one gives you 0, that one gives you 1, so that gives you 1. So therefore, the limit of Sn is equal to 2. Alright. So with those main theorem that I have discussed, we have one or two theorem that I have discussed. I think the one that might confuse a little bit is that the first theorem, that we take a limit of if the given sequence is if the given series converge, then the limit is 0. The limit of un is 0. But if the limit of un is 0, then we cannot make any conclusion on the divergence or convergence of the series. And on top of that, if the limit of un is different than 0, then we can find that the series diverge. Okay, so for the next I think we have another 3 hours to go, and I have time to discuss on the convergent test. Yeah, so we have comparison test, we have ratio test, and so on and so forth. I will discuss all those things in the next video. So for now, bye bye, thank you.